Hello, good morning, all of you. Today, I would like to discuss that is moving charges and magnetism. So, first of all, you have to know the effects of electric current. So, you are already familiar that while discussing the current electricity, as I discussed about the what are the effects of electric current. The first effect of electric current is that heating effect of electric current. And what is the heating effect of electric current? Whenever a conductor carries current, that conductor will going to get heated, or whenever passing current through the coil will going to get heated. This is nothing but the heating of effect of electric current. So you are already familiar that iron, electric stove, these are the examples for the what heating effect of electric current. Similarly, that is magnetic effect of electric current, that is mechanical effect of electric current, chemical effect of electric current. Like this, we'll find that effect of electric current. So today, we would like to discuss about the magnetic effect of electric current. So this is nothing but the moving charges and magnetism, is it? So what is the magnetic effect of electric current? So whenever you are passing current through the conductor, surrounding to the conductor, a magnetic field is going to develop, which is known as the magnetic effect of electric current. So that means that on the basis of definition of electric current, we can define that the flow of charge per second, which is known as the what electric current, is it? So flow of charge, that is flow of charge is nothing but the moving charge through the conductor which produces the magnetic field. This is nothing but the moving charges, is it? Because of charges flowing through the conductor, surrounding to the conductor or around the vicinity of the conductor, we will find the magnetic field. So if the magnetic field is going to produce surrounding to the conductor, so it will be vary from the point to point from the conductor. So in order to exactly calculate the magnitude of magnetic field, so two scientists, that namely Bayes and Savarts and Laplace, these two scientists independently they were formulated in a formula. With the help of that formula, we can find the magnitude of magnetic field at different point in the magnetic field domain. So the basic purpose of this Bayes-Savart's law, or else you can say that Laplace law, is to determine the magnitude of magnetic field around the conductor. So imagine that here we have considered that XY conductor. In this XY conductor, you are passing that some current from X to Y direction. As a result, whenever the conductor carries current through current, is it either in upward direction or in the downward direction? So what happens that surrounding to this XY conductor, a magnetic field is going to develop. That magnetic field or magnitude of magnetic field or intensity of magnetic field, it varies from point to point, or it varies as you are moving away from the conductor. See, as you are moving away from the conductor, magnitude of magnetic field that will going to decreases. When you are coming toward the conductor, magnitude of magnetic field is going to increases. So that means that to know the exactly, so at this point separated from the center of the current element, say that say A represents the distance between point P and center of the current element. As this distance increases, what happens? The magnitude of magnetic field, where dB represents the magnitude of magnetic field, is it? So if I increase the length of this current element, whether the magnitude of magnetic field increases or decreases. If I increase the current through this conductor, what happens on the magnitude of magnetic field. All these factors will go to study under the Biot's and Savart's law, or else you can call that Laplace law. As you know that this is an experimental law, is it? So let us see the magnitude of magnetic field at the different point of the conductor depends on what factor. First of all, the magnitude of magnetic field at the point P is directly proportional to the strength of electric current which you are passing through the conductor. As you are passing more current to the conductor, you will find the more magnetic field at the point P. As well, second factor is that, as I said, that directly proportional to the current. I mean that magnitude of magnetic field, it is directly proportional to the strength of electric current. If the strength is more, what happens that magnetic field is also more. Strength of electric current is more, magnitude of magnetic field is more. If the strength decreases, strength of electric current decreases, magnetic field is decreases. This is the content of the first factor, that is magnetic field is directly proportional to the what current, is it. Second factor is that this dl, this is the AB of length dl, is it. This XY conductor, so it is divided into segments. So among these segments you are consider one small portion of the conductor, that is AB, which is having length dl. So this current element, what is the current element? It is the product of current and the small portion of the conductor which is known as the what? Current element. So the magnitude of magnetic field at this point P, so it is also depends on the what? That is dl. As the length of this conductor goes on increases, magnitude of magnetic field at this point is also increases. You see. Similarly, third factor, as I said, is directly proportional to the length of the dl. You see. Now, third factor is that it is directly proportional to the theta. What is the theta? It is the angle between the what? AB conductor and line joining the point P to the center of the current element. You see that in these these 2 points. So this is about the line joining point P and center of the current element. So this is about the plane of the conductor. So between them a angle will go to form. Sine of the angle between the what? Line joining point P and center of the current element. So that means that third factor is directly proportional to the sin theta. As the theta increases, magnitude of magnetic field at this point is also increases. Now lastly, the fourth factor, that is magnitude of magnetic field at the point P, it is inversely proportional to the square of the distance between the point P and center of the current element. So you can say that O is the imagine that this O is the center of current element. So as inversely proportional to the square of the distance between the point P and center of the current element. That is, it is inversely proportional to the square of the distance between the P and center of the current element. So these are the 4 factors are there. So with these 4 factors, what we will find? So these are the experimental points which were evaluated, which were discussed by these Laplace. Is it? Now let us see. I want to know that. I don't want to see that. So I am maintaining that particular conditions. Say this is an XY conductor. So in this conductor, your definite some current you are passing through this conductor. This conductor having current element length is say that 5 centimeter. Is it 10 centimeter, whatever it may be. So definite length of the conductor is that. So as a result, surrounding to this conductor, so a magnetic field is developed. So this circle represents the domain of the magnetic field. In this domain of the magnetic field, so I would like to know the magnetic field from the magnetic field at different point from the conductor. Is it? So what happens that, say as we are moving this point away from the conductor, magnetic field is going to, magnetic field or strength of magnetic field goes on decreases. As you are moving toward the, that is conductor, as you are very closer to the what this conductor, magnitude of magnetic field that will going to decreases. You see, I mean that as you are moving towards the what conductor, magnitude of magnetic field is going to increases. As you are moving away from the conductor, magnitude of magnetic field is going to decreases, because it is inversely proportional to the square of the distance between point P and center of the current element. Now, on clubbing these four factors, say that I can write it as dB represents the magnitude of magnetic field, which is directly proportional to the strength of electric current. So, first factor is dB is directly proportional to the current. Second factor is that is dB is directly proportional to the length of the current element, that is nothing but the dl, is it? And third factor is that it is directly proportional to the sine of angle between the what? Angle between the line joining point P and center of the current element and what is that? This current element, is it? So, lastly, inversely proportional to the square of the distance between point P and center of the current element. As this A goes on increases, what happen that magnitude of magnetic field, what happen that it will go to decreases. You see. So, since it is inversely proportional, so therefore that is distance between point P and O, that is nothing but the R square. So therefore it is inversely proportional. So therefore as I written that A square. Now you see that this expression associated what proportionality symbol. So you have to eliminate it. In order to eliminate it, you have to take a constant of proportionality. So that is, you can say that dB is equal to K ideal sin theta upon E square. So now question is that what is K? K is a proportionality constant value. So it is evaluated in SI system, that is mu naught upon 4 pi. So that means that in place of K I can substitute that what mu naught upon 4 pi. Then what is the mu naught? Mu naught is the permeability of the what? Permeability, absolute permeability. So mu naught is equal to, can write it as 4 pi into 10 to the power minus 7 ampere, Tesla ampere. So this is the mu naught value, right? So now let us see. You can see that you consider this expression. You got it? So you are taking that mu naught is equal to, either you can write it is, that is K is equal to mu naught upon 4 pi, or that this mu naught value also you can write it ultimately. So you write it is K is equal to mu naught upon 4 pi. So this is an simplified form of this expression. Now you say that when the magnetic field is going to, you see that from this figure, what we conclude that as theta increases, magnitude of magnetic field, it will going to increases. So sign of that. So now let us see. It may not necessarily that it should be what always 90. It may vary from, it may be less than 90, or sometime it may be more than 90. When the magnetic field will be maximum. When the magnetic field is maximum. When theta is perpendicular to, I mean that angle between this line and this line is exactly 90 degree. During that time, magnitude of magnetic field is going to increases. So that means that if you treated that theta is equal to 90 degree, so sin 90 is equal to 1, you are already familiar that. So therefore in this expression I can substitute that in place of sin theta. So I write it here in place of sin theta. So that is dB, which is equal to mu naught upon 4 pi into ideal, so into 1. because sin 90 is equal to 1. Therefore, as I written that 1 divided by a square. So with this expression, I can find out the magnitude of magnetic field at a different point from the conductor. So that point P point you can shift at this position. Say that this is the word the P1. So you see that P1, the distance between P1 and center of the current element, this goes on changing as we are moving away from this midpoint of the current element. So according to this factor, so magnitude of magnetic field goes on decreases. So at this point, what happens? Magnitude of magnetic field will become 0. It is almost 0, is it? So now let us see what I want to tell you. Is it? This is what with this expression we can find the magnitude of magnetic field. So this its value V0 upon 4 pi. It depends on the system of unit chosen. Is it? So now if it is what in air medium, so its value is V0 upon 4 pi. So with this expression I can write it is with this expression I can find the magnitude of magnetic field at a different point from the from the conductor in which current is flowing. Is it? The basic thing is that so whenever you are maintaining these conditions, and these conditions from different points from the conductor, what is the magnitude of magnetic field, you can evaluate by using the Biot-Savart's law, or else you can call that Laplace law. Let us see this is a basic law. I would like to shift to the another important bit, that is direct application of this this theory, Biot-Savart's law, that is expression for magnetic field at a point on the axis of the circular coil carrying current. So it is an important bit for the examination point of view as well as for the knowledge point of view. So therefore, I would like to write the title, that is expression for magnitude of magnetic field at a point. Say this is what expression for magnetic field at a point on the axis of circular coil. Expression for magnetic field at a point on the axis of circular coil which carries current. The content of this is the most important expression. Usually alternate year this will going to ask for 5 marks. Let us see what you want to know, that expression for magnetic field at a point on the axis of the circular coil. So that means that what it tells that you have to consider a circular coil. So on this circular coil, you have to consider a circular coil. In this circular coil, you have to pass that circular coil carries current. What is it? Which carries the current. So as a result, whenever you are passing current through any coil, a magnetic field will going to develop. So in this case, what you want to this question tag, what it demands that, so you have to find an expression for the magnetic field at a point on the axis of the circular coil. So that means that first of all you have to draw the circular coil. You have to consider the circular coil. So this is a circular coil, is it? For every circle there is a center. So imagine that O is the center of this circular coil. So this circle having certain radius, say that r represent the radius of the circular coil, r represent the radius of the circular coil. So you have to, according to that question, expression for magnetic field at a point on the axis of the circular coil. So this is a perpendicular line which is passing through the center of the center of the coil. This is nothing but the axis of the circular coil. So on this axis of the circular coil, you have to find say this is a point. You have to consider a point P. So which is separated from the center of the current element. It is nothing but the x. I mean the distance between the center of the current element and the point P, that is nothing but the x. So at different point, I would like to at this point say on the axis center of the current element to the on this axis 5 centimeter, 20 centimeter, 30 centimeter, different distance. What is the magnitude of magnetic field? So if you want to evaluate a different point, so you need an expression. So you want to say that obtain an expression for magnetic field at a point on the axis of the circular coil which carries the current. So this is you are considering a circular coil. In this circular coil you are passing the current either in the clockwise direction or in the anti-clockwise direction. As a result, surrounding to the conductor, what happens surrounding to the coil, a magnetic field is going to develop, is it? So on the axis of the, you have to consider an what? So this is an axis of the circular coil. On the axis of the circular coil, you are consider a point which is separated x distance from the center of the current element. So now imagine that. So according to the title, what it says that, so you are passing the current in the, say that in a clockwise direction, I ampere of current you are passing in the coil in the clockwise direction. So now what happens that, so what you have to do that, this circular coil is divided into small segments, is it? So this is what AB is a small current, small portion of the coil. So this AB is a small portion of the coil having length dl. So AB is a small portion of the circular coil having length dl. Similarly, exactly opposite to this AB, another current element you have to consider, that you can say that A dash, B dash is the another current element having length is dl. So that means that these two elements, how are they are looking? Exactly diametrically opposite to each other. This current element is exactly opposite to what? A dash, B dash. So therefore these two current elements we are calling that diametrically opposite current element having same length. So AB is a small portion of the conductor having length dl. Similarly, you have to consider identical current element, that is AB, A dash, B dash having length same as that of the AB, is it? So what you have to imagine that, so in the first stage what you have to do that, because of current passing through this small portion of the conductor, how much magnetic field will produce at this point. Similarly, so once current pass through the AB current element, we will find the some amount of magnetic field at this point. When the same current passes through the A dash, B dash, we will find once again magnetic field at the point P. I mean that because of whenever the current passing through these two current elements, you will find some magnetic field at the point P. So if you imagine that this whole circular coil is made up of such diametrically opposite element, how much is the how much is the magnitude of magnetic field, or else you can say that strength of magnetic field at the point P. In order to find the magnitude of magnetic field on the axis of the circular coil, which is separated from the x distance, x distance from the center. So what you have to do that, you have to complete this figure. So this is the midpoint of the current element to the This is what distance between point P and center of the current element, which is represented as A. Right? So now this is a 90 degree. So this you can say that alpha, is it? Now you have to draw a perpendicular line, is it, which is perpendicular to the axis of the circular coil and passing through the point P. So this is a perpendicular line which is passing through the what? P. So this you can say that y-axis, this is negative y-axis, right? So this is acting in the downward direction, this is acting in the upward direction. Now let us see. So first of all, what you have to do, there are 4 steps there. I would like to, I don't just as I described that, you are consider a coil of mean radius, you are consider a coil of n turns, not single turn. There are n number of turns are there, is it? So having mean radius r. So n represents the number of turns, is it? Where r represents the mean radius of the such turns of the coil, is it? So now at this point I would like to find the magnitude of or strength of magnetic field due to current passing through. Say that I ampere of current is continuously flowing through the what? Circular coil. So what is the magnitude of magnetic field, or else you can say that strength of magnetic field at the point P. So that is the what the demand of this question. You have to obtain an expression for the magnitude of, you have to obtain an expression for the magnetic field at a point on the axis of the circular coil. That circular coil carries the definite current. So see what you have to do that. This is about the description of the figure. Now you consider that AB current element. So you consider AB current element. Say in the AB current element, say that I ampere of current is flowing. So as a result, at this point, what is the magnitude of magnetic field? I mean that because of current flowing through the small portion of the circular coil, what amount of magnetic field you will find at the point P? So first step is that, step 1, the magnetic field at the point P, magnitude of, or else you can say that my magnetic field at the point P, magnetic field dB, magnetic field is denoted by dB, magnetic field at point P due to AB element of length dl is, I mean that magnetic field dB at point P due to AB element of length dl. I mean that this is nothing but the current element, you can say that. Because of current flowing through this current element, what is the magnitude of magnetic field at this point? So you are already familiar that by using Laplace law, you can find the what magnitude of magnetic field. So as you know that that is from Laplace law. So from the by Laplace law. So what is say that dV is equal to mu naught upon 4 pi. This is the k value, proportionality constant value. It directly proportional to the strength of current element. Just you have seen that 4 factors. That is magnitude of magnetic field at this point P directly proportional to the strength of. If you pass that larger current, you see, you will find the more magnetic field at the point P. So similarly, it also depends on the size. So size you can say that 3 centimeter, 5 centimeter. As size, I mean the dl size goes on changes, dv is also changes. So therefore, it is directly proportional to the what dl. And third factor, as you are aware of it, is directly proportional to the sine theta. So sine theta, and inversely proportional to the square of the distance between the midpoint of the current element to the point P, which is nothing but the A, is saying that square of the distance between, that is A square. So you see that here angle is theta is 90 degree. For the 90 degree, when theta is equal to 90 degree, sin 90 is equal to, as you are aware of it, sin 90 degree, which is equal to 1. So therefore the above equation will become what? dB is equal to mu naught upon 4 pi into IDL, because sin 90 is equal to 1. So therefore I will write it 1. No need to write it. That is what? A square. So now the question is that, so this magnetic field at this point is going to act in which direction? So this will act in this direction. Say along PM direction, magnetic field is going to act. This is an M, right? So because of this current element, you will find the direction of magnetic field is going to act along the PM. This arrow represents the direction of magnetic field, and apart from that, it does also represent the what? Magnitude of magnetic field. Now same current, it is going to comes down and it passes through the A dash B dash having length dl. Since that is the size of this A dash B dash is similar to that, so that means that same amount of current, same amount of magnetic field you will find at this point, but the direction of its magnetic field is going to opposite to it. So that means that we can join this this line. Is it? So this is the center of the current element. So from the center of the current element, the distance between point P and center of the current element, it is nothing but the A itself. If it is the case, so when the current passing through this current A dash B dash current element having length dl, what amount of magnetic field produced at this point is it? So that is similar to this. That means that similarly I can write it is similarly magnetic field at P due to what? Due to A dash B dash current element of length